Welcome to an online lecture on preparing data for analysis. This lecture will help you prepare for your first assignment. So before we can run any analyses, we need to ensure that our data set is properly prepared. This is a very important aspect of the analysis process, and we call this data cleaning. So data cleaning involves a series of very specific steps. And in most cases, researchers will spend most of their time preparing their data set and only a small portion of their time on the actual analyses. So when conducting data cleaning, we have a number of procedures that we need to follow. So we need to first check for impossible and out of range values. Then we need to check for response sets. Next, we need to deal with any missing values. We have to manage our outlier scores. We need to check the assumptions for the statistical analyses that we're going to run. And we need to check for reliability if we're going to be using any scales or anything that should require reliability analyses. So we'll go through each of these here, starting with impossible values. So when we're looking for impossible or out of range values, we're looking for something that is not within the range of possible answers or something that's possible for a given question. So one of the best ways to detect whether we have any impossible or out of range values is to look at the frequency tables and identify responses that are invalid. So for example, using this life satisfaction scale here, the possible values are 1 to 5. So we can see in the frequency table that we have 1, 2, 3, 4, 5, and a 9. So there's something wrong here because 9 isn't part of the 1 to 5 scale. So this is an easy way to detect any of these values. So what you can do if you run into any problems like this is if you have access to the original data, or if the error is an obvious typo and you know what should have been there, you can actually just make the correction. However, if you have no way of knowing what the value should have been, you should remove it and code it as a missing value. So for example, if, let's say that it should have been a 5 and for whatever reason you have a T, then you can probably assume that's just a typo on the keyboard since the 5 and the T are next to each other. However, if you really have no way of knowing, you should just remove the value. Okay, next we're looking at response sets. So these are a lot more difficult to detect. And essentially, a response set occurs when participants do not complete the questionnaires properly. So this could be really anything. Some participants are just not interested in completing the survey or participating, so they might just enter 1s or 7s the whole way through. So it's really important to ensure that these participants are not included in the analyses, if possible, since they will skew the results. So the only way to detect response sets is to look at the raw data and look for any suspicious patterns. Like I said, it's very difficult to detect, and one way to help with this is to include trick questions to ensure that the questionnaire is completed properly. So an example of a trick question could be, please enter or respond to this next question with a 4. And anyone who doesn't have a 4 for that question presumably did not read the question, and you can assume that they didn't read the questionnaire all that closely, and you might want to consider removing them. So when you're looking for response sets, you are literally scrolling through SPSS and just looking through the patterns of data and looking to see if there's anything unusual. In this particular case, this participant selected 4 for every response. So would this be enough to qualify as a response set? That would be your judgment call. However, if they've entered 4 to some questions that really don't even make sense to have a 4 and are literally just going 4 across the board, then it's probably assumed that they weren't really reading the questions and you can remove them from the data set. So if you can remove them, take them out. If you're not sure, then you should leave them in. Okay, missing values. So this happens pretty often. And so participants can have missing data for a number of reasons. It could just be, measurement error, they decide to skip a question, whatever. Either way, we do need to manage it, and we have to report how it was managed. So when you're looking for missing data, it's very easy. You just look at the frequency tables for all the variables, and the number of missing data will automatically be indicated. So for example, if there are blank cells, then you will have a row that appears here as missing. Or if you have blank cells that you've already coded in SPSS as being missing, this will show up in the same way. So what you can do to treat missing data, before we get there, we should note that dealing with missing data is very controversial and gets a lot of attention in the research. So there are a lot of different ways you can handle missing data, and generally speaking, the best way to handle it is based on whether there's a pattern underlying the missing data or whether it's missing at random. One way in SPSS to check this is to run a missing values analysis. However, and then based on that, you can impute or generate new data to replace the missing values. However, for our course, we will just focus on some of the more simple methods. So if you're going to be doing something for publication, it's not recommended that you do the methods that we're showing you today. However, for the purposes of this course, these traditional and simple methods are more than acceptable. However, if you're running real analyses that you would like to have published, then you should look into some of the best ways for handling missing data according to the patterns of missing data that you have. All right, that being said, our options for handling missing data depend on the type of variable. So if any demographic information is missing, you can't modify it, so simply assign it as missing in SPSS, usually a 99 or a 999, or you can just leave it blank. SPSS is going to treat it the same way. So demographic information like someone's age, their gender, etc., just leave it blank. If you run into nominal or ordinal variables, and the values represent more than 5% of the missing data on a particular variable, and again, the frequency table is going to tell you what percentage of the data is missing, you can create a new category of people who are not disclosed and examine them separately. However, if the missing data represents less than 5%, they can be left missing like the demographic variables. So you can just leave it, and that's fine. Okay, so things get a little bit more interesting when you have interval or ratio variables. So this is anything measured on a Likert scale or anything like reaction time or something measured on a ratio level. So missing values on interval and ratio variables can be replaced with the mean score for that particular variable. So this is called mean replacement. So step one is to calculate the mean for the variable with the missing data. So let's say that we have a mean score of 3.31. Then we would go into SPSS and replace the missing values with the mean value. So you can see here we have been replacing the missing scores with 3.31, which is the mean. Next, we need to deal with our outlier scores. So outliers are observation points that are very distant from the other observations, and this applies only to interval and ratio data. So they can occur for a number of reasons, but they may be due to measurement error. Since outlier scores can drastically bias results, it is important to manage them. So for detecting outliers, we can either do it graphically using histograms or box plots, or we can do it statistically using the Z distribution. So if we're doing it, before we go there, outlier scores exist at different levels within a given data set. So we can have univariate outliers, bivariate outliers, or multivariate outliers. So univariate outliers occur when we look at just the distributions of single variables, so just one variable. Bivariate outliers occur when we look at the combination of two variables. So you might have no outliers when you look at the scores individually. However, if you were to combine the scores, you might run into some outliers there, and those would be bivariate outliers. And then finally, multivariate outliers are similar to bivariate outliers, but we have more than two variables that we're looking at. For this course, we will just focus on univariate outliers, so outliers occurring on one single variable at a time. Okay, so how do we detect outliers? Well, we can use graphs. So like I mentioned before, you can use histograms or box plots. So as you can see here in the histogram, we have the distribution of scores, and then we have this one score here that looks clearly different than the rest. And the box plot as well, we have the rest of the scores, and we have this here. Okay, so an observation there. So in both cases, it's pretty obvious that we have one observation that's very different than the rest. There they are. So we can also use statistics to detect outliers, and this would be done through using the standard distribution, so the z-scores. So you may recall that for z-scores, 95% of the scores are going to fall between negative 1.96 and positive 1.96, and then 99 are going to be between negative 2.58 and positive 2.58, and then 99.9 are going to be between negative 3.29 and positive 3.29. So we can use this to help determine how far from the center, so how far from zero, certain observations fall on a given variable. So again, we're looking for unusual scores. So in statistics, we have agreed that expected scores, so not usual scores, not unusual scores, fall within 95% of the middle. So that would be between negative 1.96 and positive 1.96. And that anything outside of here, so 2.5% on this side, 2.5% on that side, would consider to be unusual, so therefore an outlier. So to determine this, we need to convert our raw scores into standardized z-scores to determine if they are unusual. And what we're looking for are values that are bigger or smaller than positive or negative 1.96. So we have here the following examples of reaction time. So we have 1, 3, 5, 6, 10, 12, and 15. And we have converted these into z-scores, so standardized scores. And we see that for 1, we have negative 1.18, and then we have negative 0.27, etc., working our way all the way up to 5.18. So if we use the cutoff of plus or minus 1.96, so 95%, we can determine that the reaction time scores of 10, 12, and 15 are outliers. So 10, 12, and 15 seconds is an outlier given that these scores here, so the z-scores, are bigger than plus 1.96. Okay, so what can you do if you run into outlier scores? So the best option is something called Windsorizing, where you would substitute the outlier score with the next closest value that is not an outlier. So if you recall, the z-score formula is a rearranged formula of this. However, if we want to determine in our raw scores what is the most extreme score but still in range, we would have to use this formula. So for the example we just had, the reaction time standard deviation is 2.2 seconds and the mean is 3.59. So what we're looking for is the score that's the most extreme but still in range. So if 1.96 is an outlier, it means that the next closest score is going to be 1.95. So that's the Z. So what we do here is we're going to replace Z with the score that we want, so 1.95. Replace this here with our standard deviation, 2.2, and then this here is the mean for our sample, so 3.59. So if we do 1.95 times 2.2 plus 3.59, we get 7.88. So that means that we would replace the scores of 10 seconds, 12 seconds, and 15 seconds with 7.88. So this means that these scores are right on the edge at z-scores of 1.95, but they are not at that cutoff of 1.96, so they're still within range. Sorry, just a note on this. With outliers, it's best to only just do it once, because as you replace these scores, the distribution is going to change. The mean is going to be slightly different, and the standard deviation is going to be slightly different. So if you were to keep doing this, you would be able to keep trimming, and eventually you would end up with just everything in the middle. So you just need to do it one time. Okay, so next we need to check for our assumptions. So the tests, or the analyses that we're going to be seeing later in this course, are all parametric tests, and they're based on a normal distribution of data. So the assumptions of these tests include normality, which makes sense, linearity, homoscedasticity and homogeneity of variance, and independence. So we'll talk quickly about each of these today, and we'll be seeing some of them a lot more closely later on in the semester. So the thing with these assumptions is that depending on the analysis you're running, these assumptions need to be met before you can proceed with the analyses. So in some cases, if you haven't met the assumption, there are no corrections you can make, and you just simply cannot perform the analysis. In other cases, there are options, and you can make certain modifications and deal with the violation of the assumption and then proceed with the analyses. So looking at each one separately, first we have normality. So if you recall, normal distribution looks something like this, and it is relevant to estimating parameters, confidence intervals, our null hypothesis tests, and errors. So does it mean that all of our variables need to have a normal distribution? No. So what we're looking at is that each level of the other variable has a normal distribution. So here's an example. We have the reported stress of university students. So if we were to just plot all of our university student stress levels, we see that there's some low, and then it kind of spikes about here, and then it drops off again. So let's say this is like a 2 out of 10, and then it dips again, and then 5 out of 10, etc. And so we see here there's waves. So it appears non-normal. However, if we were to break down this same variable by year of university, what we see is that our first years are significantly less stressed than our second years, and our second years are less stressed than our third years. But what's important here is that each of these groupings has its own normal distribution. So that's what's important in the assumption of normality, is not that an individual variable is normal, but that when we're crossing two variables, so when we're looking at two different things, it's important that the variable be normal for the other levels of the other variable. So something like this. So what we have are actually three normal groups. So really though, with normality, it only is really important with small samples, because the central limit theorem, which states that as we have more samples, the distribution of means will increasingly become normal. It allows us to forget about normality with larger samples. So in more practical terms, as long as the sample is fairly large, outliers are more of an issue than normality. So you don't need to worry so much about normality and just treat the outliers. However, there are different ways to detect normality within a particular variable, and you should always look at these. So the first is the eyeball test. So you can just inspect the histogram. The next is to calculate skewness and kurtosis. And also finally, the third one is to do a formal normality test. However, for this course, we will only use 1 and 2. Okay, number 3 you won't need to worry about. So using the eyeball test to detect normality, like I said, if the sample is larger than 300, you can just kind of not worry about it, but you can also just look at the histogram. So we have reaction time here. You can see that it's approximately normal. Doesn't look too bad, so you're probably good to go. Using skewness and kurtosis to detect normality. So this is what you do when you have a smaller sample size, and the way you do it is in SPSS, you can ask SPSS to generate or calculate skewness and kurtosis, and it's going to give you the statistic and the standard error for both of them. So you see here we have skewness statistic 2.135, and the standard error is 0.241, and same thing for kurtosis. So what we're looking for is we need to calculate the skewness ratio and the kurtosis ratio. So we divide the statistic by the standard error, and then we interpret the resulting score like a z-score. So for example, so the z-score of skewness is 2.135 divided by 0.241, and we get 8.86. And kurtosis, we do 8.223 divided by 0.478, and we get 17.20. So the way we interpret this is we use the same cutoff values that we would use for interpreting outliers, where we want to, or the score associated with 95% is positive or negative 1.96, and etc. So for small samples of less than 50, you would use the z-score cutoff associated with 95%. So essentially, if you have skewness or kurtosis values that are higher or bigger or smaller than this, you would assume that you have an issue with either your skewness or your kurtosis. Once you're at a larger sample, you would use the cutoff associated with 99%. So, 99.9% is what it should say, which is 3.29. So our sample had 100 participants, and we obtained a value of 8.86 for skewness and 17.20 for kurtosis. Both exceeded the cutoff of 3.29, so we can conclude that our data is both positively skewed and had positive kurtosis, and we associated that with the positive value we obtained here. So if you recall, positive skew looks like this, and positive kurtosis looks like that. So what we have is kind of a pointy, very pointy, skewed distribution. So options when you violate the assumption of normality. So the easiest solution to non-normal data is to use tests that do not require non-normal data. Bootstrapping is also an option. However, we won't be doing that in this class. And you can also use mathematical transformations to make it a normal distribution. So for example, you could use the log scores, or you could do the square root, etc., and it would transform it into a normal distribution. But as I mentioned, we won't adjust for normality in this class, since we are not going to be we're not too worried about univariate normality. Anyway, sorry. However, you do need to know how to calculate the skewness and kurtosis ratios. Okay, so the remaining assumptions are linearity, homoscedasticity / homogeneity of variance, and independence. We're going to learn more about their detection and interpretation later in the course. However, here is a quick overview of what they are. So linearity talks about the outcome variable being linearly related to the predictor variables. So the amount of change between scores on two variables should be constant for the entire range of scores for the variables. So a linear relationship would look something like this. If this is variable A and this is variable B. If the relationship is nonlinear, the statistics will assume it is linear and underestimate the strength of the relationship or fail to detect the relationship. So if we have something like this and the statistics are testing for this, the statistics aren't going to find this. They're not designed for that. So one of the assumptions is this. Homoscedasticity and homogeneity of variance have to do with testing several groups of participants, and what we're looking for is the same amount of variance or error with each group. So in correlational designs, the variance of the outcome variable should be stable at all levels of the predictor variable, and not meeting this assumption will impact the parameter estimates and will cause problems when we're doing null hypothesis testing. So what does homogeneity of variance or homoscedasticity of variance look like? Well, let's say we have our example of first year, second year, and third years, and we have their stress levels. So in a case where we have homogeneous variance, we would expect to see a similar scatter of scores for each of the three groups. So we see here that there's about this much variability in first years, this much variability in second years, and this much variability in third years. So they have similar amounts of error, so similar standard deviations, even if their means are different. However, if we have heterogeneous variances, so it means they're not the same, what we might have is a larger standard deviation here compared to here, and then an even bigger standard deviation there for these groups, meaning that the scores vary a lot more. So this would be a problem. This is what we're looking for. So to assess homogeneity of variance, there is a test called Levene's test, and what it does is it tests if the variance in different groups are the same. So if we have a problem, if we have significant results for Levene's test, it means that we have a problem and the variances are not equal. What we're looking for this test is something that's not significant, and we'll get to this later in the semester. Okay, finally, independence. So this has to do with the fact that the errors in our model should not be related to each other, and the best way to explain this is to give an example. So a statistics test is given to students to assess their comprehension, and any errors executed by the students on the test will be the result of a lack of knowledge, lack of question comprehensions, or a performance error. These errors are not associated with anyone else's performance on the test. They are independent. So let's say that two students copy off of each other. These students' errors are now associated with each other and are no longer truly independent. So it means that the likelihood of one of those two students committing an error was no longer just related to their own knowledge or their question comprehension or their performance, but it was also related to the other student committing an error. So what we're looking for in our data is that there is no underlying relationships between the variables that are not already assumed in the analysis that we're doing. So for example, if we ask people to complete a questionnaire at the beginning of the semester and again at the end of the semester, we expect that the errors are not independent, because it means that people's scores the first time should be associated with their scores the second time because it's the same people. However, if we ask males and females to complete questionnaires, we would not expect there to be a relationship between the errors, since males and females are not the same people. So that's where it should be more separate. So if this assumption is violated, confidence intervals will be impacted, and significance tests or hypothesis tests will be invalid. So the final thing we need to look at is the reliability of our measures. So what we're really looking for is we want to ensure that our measures are looking at the same thing. So this more has to do with when we administer a psychological scale or a measure where we might have a few different questions that are supposed to be assessing the same thing. So let's use this example of 4 questions that are supposed to measure the extent that, they're supposed to measure whether someone agrees about these statements about their relationship using a 1 to 5 scale. So it's a relationship satisfaction scale. So we have item 1, I am satisfied with my current relationship, and people can answer using a 1 to 5 scale. Then we have number 2, my partner makes me happy. Number 3, I feel great when I'm with my partner. And number 4, I like bananas. So if you run a reliability test, the test should let you know that this question is not like the others. So these 3 are measuring the same underlying construct, but this one is not. So to determine this, we calculate Cronbach's alpha, which is a measure of internal consistency. So what it will do is it looks at the correlations between variables, and what it's looking for is a higher intercorrelation. And based on that, so the higher this intercorrelation is, the higher the Cronbach's alpha coefficient will be. And the higher that value is, the more you can trust that the items are measuring the same underlying construct. So the rules of thumb for interpreting a Cronbach's alpha value are that 0.9 to 1 are excellent fits. And sorry, I should mention that Cronbach's alpha can go from basically anywhere from -1 to +1. However, if you have a negative value, it means that one of your scores is not even, or one of your variables isn't measured in the same direction. So generally speaking, you should have something between 0 and 1. If you have a negative value, there's a problem with one of your variables. 0.7 to 0.9 is a good fit. 0.6 to 0.7 is acceptable. 0.5 to 0.6 is poor, and then anything under 0.5 is unacceptable. So one thing that should be noted is that one thing that'll help increase your Chromebacks alpha value is to just add more items. So it's harder to have excellent fit, for example, if you only have 3 items. However, if you have 8 items that all measure approximately the same thing, you're going to find scores in the 9s easily. Okay, so that is it for the lecture on preparing data for analysis. And if you take a look at the accompanying SPSS tutorial, you should have all of the instructions you need for your first assignment.